We are still on hypothesis testing, and your homework after this lecture is going to be working some problems. So I'm going to work some problems for you and with you, and then you're going to work some problems for your homework. In this scenario, a nutritionist researcher is interested in whether Native Americans eat more sugar than what's recommended, and she knows what the recommendations are. Her group of 25 Native Americans, I'm giving you this information this time. We don't have to compute information from the sample. But her group of 25 Native Americans ate 19 teaspoons of sugar each day on average, and she's wanting to know the range of means that likely include her population mean for the average sugar consumption among Native Americans. Let's recall how it works. We're going to start with a question, something to do with Native American sugar consumption and the recommendation for sugar consumption. We're going to turn that into a research hypothesis, which we will turn into an alternative hypothesis. And then the null hypothesis will be everything that the alternative hypothesis is not. We're going to test the null. We have to choose a test statistic, determine the location of the critical region, and determine the size of the critical region. Most people use alpha 0.05 most of the time, so that's what we'll be using. We're going to reject or fail to reject the null hypothesis, and from that, we're going to form conclusions. So the research question, do Native Americans eat more sugar than the amount recommended, is turned into a research hypothesis, which is just the research question turned into a statement. Native Americans do eat more sugar than the amount recommended. And then we turn that research hypothesis directly into an alternative hypothesis. So mu, the population mean for Native Americans, is greater than the population mean for what is recommended. And the null is everything that the alternative is not. So mu for Native Americans is less than or equal to mu for what is recommended. From the statement, the research hypothesis that Native Americans eat more sugar than the recommendation, we know that we are going to have directional hypotheses, and that's going to result in a one-tailed test. From the statement that she wants to know the range of means, we know that we're going to have to compute a confidence interval. Because she knows, which means that we have population information, she knows that the recommended number of teaspoons of sugar is 6 with a standard deviation of 1. Because she knows that that standard deviation is 1, we know that we have sigma, and we can use the z distribution. With a one-tailed test, we have a confidence interval that is either to the right and includes infinity on the left, or an interval that ends on the left and includes infinity on the right. So we've got to pick whether we use a plus sign, a positive z critical, or a negative z critical. We think, the researcher thinks, that Native Americans are going to eat more sugar than what is recommended, which is the same thing as saying that the recommended amount of sugar intake is going to be less than the amount of sugar intake for Native Americans. The mean for Native Americans is 19 teaspoons. So if the recommended mean, like her alternative hypothesis says and her research hypothesis says, is less than that, then we need to cut to the left to determine whether mu recommended is more different, so much lower than 19 teaspoons that we would not expect the mu for the recommendation of 6 teaspoons to be the mu also for Native Americans. Because alpha is 0.05, we know that 5% of this distribution is going to be in the tail beyond the cut, and 95% of this distribution will be in the body. Z critical for a one-tailed test is 1.65, and because it's to the left, it's a minus 1.65. So now we form the confidence interval, a one-tailed confidence interval using minus 1.65 for Z critical. So the mean for Native Americans, the sample mean, is 19 minus 1.65 times 0.2, and that is 18.67. That's where we cut 18.67. That's the sample mean that is 1.65 standard errors to the left of 19. We would not expect the population mean for Native American sugar consumption to be any smaller than 18.67 because the recommended amount of sugar intake is 6 teaspoons, and that's less than 18.67 teaspoons, less than what we would expect to be our population mean for Native Americans. We have to reject the null hypothesis. And our conclusion is that American Indians eat significantly more sugar each day than is recommended. Sometimes a researcher wants to test the null, but they don't need a range of means. We don't have to look for the lowest mean or the highest mean that might surround the population mean. We can just look to see whether two means are so far away from one another in terms of the standard error that they're more than the critical value, 1.96 if it's a two-tail test, or 1.65 if it's a one-tail test, more than that far away from one another, in which case we can say there's a significant difference. So let's rework, or let's work some other scenarios and just look for whether there's a significant difference without the range of means. We're also going to be introduced to t-tests. So in z-tests, we have to have sigma in order to use that z distribution, the normal distribution. But sometimes we have mu, but we do not have sigma. And that's where the t-tests come in. The distribution shape changes a little bit, goes from normal to leptokurtic with small sample sizes and no sigma. So we need to learn how to work another distribution, and that's going to be the t-distribution. Because the t-distribution is leptokurtic, the critical values for t are larger, especially with smaller sample sizes, than the critical value for z. So you should see t-criticals that are larger than 1.96 for a two-tail test and larger than 1.65 for a one-tail test. But if you look down at the bottom of the t-table where there are infinity degrees of freedom, t is exactly equal on infinity degrees of freedom to z. The t-distribution is kind of like the z-distribution, except we look up the critical value on alpha and also degrees of freedom. Remember that degrees of freedom are n-1. So at alpha 0.05, if we have a one-tail test, then we use the second column, that 0.05 column. If we have a two-tail test and we want 0.025 in each tail, then we use the third column. So if we need to compute a confidence interval, the researcher will ask for a range of means. If we do not need to compute a confidence interval and we can just do a z or a t-test, the researcher won't ask for a range of means. We have some choices now. We need to either choose to use the z-distribution, we'll use the z-distribution if sigma is known, or the t-distribution, a new distribution. And we'll use that distribution if sigma is not known. We need to choose whether we need to do a confidence interval or a z-test or a t-test. We're going to use a confidence interval if the researcher asks for a range of means, and a z-test or a t-test if she doesn't. Remember that the z-distribution is used to find z-critical, and the t-distribution will be used to find t-critical. But once we get z-critical or t-critical, the process is the same. So let's try it. You determine whether we need a confidence interval or a z-t test and whether we're going to use the z or the t distribution. So in scenario 1, a nutritionist researcher is interested in whether Black Americans eat more sugar than what is recommended. That sentence gives us the research hypothesis, Black Americans eat more sugar than what is recommended, and from the research hypothesis we get the alternative, the population mean amount of sugar for Black Americans is greater than the population mean amount of sugar that's recommended. And from the alternative, we get the null, which is everything the alternative is not. So back to the scenario. She knows that recommendations are an average of 6 teaspoons of sugar each day with a standard deviation of 1 teaspoon. What she knows is population information. She does not have to estimate that. So we know from that that she has mu for what is recommended, 6 teaspoons, and the standard deviation sigma of 1 teaspoon. From that, we know that we need to use the z-distribution because sigma is known. So we'll use the z-distribution to get a critical value. We know that it's a one-tailed test from the alternative hypothesis and the null hypothesis. So our z critical value will be 1.65. We don't know yet whether that's a plus or a minus. Let's go back to the scenario. Her group of 9 Black Americans ate 7 teaspoons of sugar each day on average. So N is 9 and X bar is 7. And we know that we are going to use a z-test and not a confidence interval because she did not ask for a range of means. So we compute z and we get 3.33. And 3.33 is greater than z critical, 1.65. So we have to reject that null hypothesis in favor of the alternative. And our conclusion is that Black Americans eat more sugar than what is recommended. And we're done. Okay, scenario 2. A nutritionist researcher, again, is interested in whether Asian Americans differ from white Americans in their fruit intake. She knows that white Americans eat an average of 2 servings of fruit each day. If she knows, then we're talking about population information. So mu for white Americans equals 2. Her group of 16 Asian Americans ate 4 servings of fruit each day on average, with a standard deviation of 2 servings. So she took a sample of 16 Asian Americans, N equals 16. She averaged their scores, and on average they ate 4 servings of fruit each day, so X bar equals 4, with a standard deviation for that sample of 2. So not sigma, but S is equal to 2. The null hypothesis, because she's interested in whether Asian Americans differ from white Americans, and she has no clue which way that's going to go. Asian Americans may eat more fruit or less fruit. She's just interested in any differences. So the alternative hypothesis is that, yeah, there are differences between Asian Americans and white Americans in the amount of fruit they eat in the population. So mu Asian Americans is not equal to mu white Americans. And the null is everything that the alternative is not. Mu Asian Americans is exactly equal to mu white Americans. Because we have S and not sigma, we know that we need to use the t-distribution and not the z-distribution. So when we look t up on 15 degrees of freedom, we get the t-critical value for a two-tailed test of 2.13. She's not asking for a range of means, so we know that we need to do a t-test and not a confidence interval. And when we compute t, we get t equals 4, and 4 is greater than 2.13, the critical value for t. So we reject the null in favor of the alternative, and we conclude that Asian Americans eat significantly more fruit than white Americans, and we're done. Here's one more, and you work through this one.